Hey, hello, welcome back. So in the last set of videos, we saw how we can derive equations of motion for different kinds of systems using Lagrangian mechanics and Lagrange's equation. So today we will be talking about two particular but very important set of terms that show up in the equations of motion. We discuss where they come from, what are their properties. So these two are dissipative and gyroscopic terms or gyroscopic effects. Before that, let's see what they are and what we're talking about. So when we write equations of motion, what we end up with is an equation like this, that I have sum of I from 1 to n. Do I use I or j? J of mij q double dot j. These are the accelerations. And very often we have these terms that are linear in velocity. So I have fij, that these functions could be functions of positions and possibly time, multiplied by q dot j. So these q dots, the velocities, are linearly multiplied by these factors fij, and we may have other hi, some other terms of q dot and t. And these ones, importantly, they don't have these linear terms. So today's topic is about these terms that show up very frequently in equations of motion. And we have many of these. So for any degree of freedom or for any generalized coordinates, we have one of these equations. So I is from 1 to n. Because of their particular form, these terms have very specific properties, and we'll be talking about two classes of these effects or terms. One of them is a dissipative effect, or coming out of a dissipative force, and the other one is gyroscopic effect. So let's get to it, and first let's look at dissipative. Let me do this. I want to do this. I unplugged my computer, see what happens, hoping that it doesn't overheat. Dissipative forces. So to see where we're coming from, let's look at one very simple example of, so this is example. Let's look at the simplest example. I have one mass moves in one-dimensional space, left and right, and I have a damper attached to it. So if you remember damper's force, this F, force of any damper is always in the opposite direction of velocity. And if it's a linear damper, we have a constant just factor multiplied by the velocity that gives us the force. And Q is my generalized coordinate, the position, the x or horizontal position of the mass. So if this is the force, I can bypass all the Lagrangian and very simply write mq double dot equals F, which in this case is minus cq dot. And from here, I see that form showing off. mq double dot plus cq dot equals 0. So this is the dissipative force that shows up in the equation of motion. And notice that it is linear in q, so something multiplied by the velocity. And another important thing to note here, the power of force F. You remember power of a force is force times the velocity by which that force is moving. And in this case, it's minus c q dot times q dot, which is minus c q dot squared. And this one is always negative. So an important property of dissipative forces are that they always subtract energy from the system. So subtract energy from system. So that is a very simple condition. Now let's extend this to these configuration spaces and equations of motion in terms of our generalized coordinates. So let's do that. So in general, let's call it in configuration space. So these dissipative forces, as the name suggests, these are non-conservative forces. They change the energy, total energy of the system, and always in this case extract energy from the system. So they are not conservative, and we have to include them as some additional forces, non-conservative additional forces in the equations of motion. And if you recall, we denoted them with some q prime I, which, if it's a dissipative force, is going to be is going to have such a form, and with a very special condition that, so something I forgot to mention, this c is how do I write this? C is a constant positive number for the force to be dissipative, to reduce energy from the system. Equivalently, in the configuration space, when we write these forces, for force to be dissipative force, the condition on these Cij should be that, well, we'll get more detail, but Cij should be kind of positive. It's not a good definition. The right definition is that, why is it missing J? For any, well, I'll get to definition in 2 videos from now. Cij should be coefficients of a symmetric positive definite matrix, which is kind of equivalent of the whole thing being positive. So that is one important kind of form that these velocity dependent terms show up in our equations of motion through these dissipative forces. So we can try to calculate forces using, first find the forces, I don't know, in Cartesian space, and then transfer those to these generalized forces. That is possible, but there is an alternative way that is more linked to the Lagrange equations and equations in general in terms of energy. So that would be maybe slightly easier to work with. In this case, if we want to work or go that route, we can define a function f, and we define it like this: 1/2 sum of I equals 1 to n, sum of j equals 1 to n. ThisCij's q dot I, q dot j. So this one is called Rayleigh, how do I write it? Rayleigh's dissipation function. So let me do this to emphasize it's something important. So we can define this, and something to note here, this F is kind of a power function, and you can kind of verify that. Power of my dissipative forces are sum of all these QIs times velocity. So force times velocity is always power, and I from 1 to n. And if I put the definition of these as a Q prime, put the definition, I have I from 1 to n, J from 1 to n. The definition was up here. So Cij Q dot J Q dot I, which is twice the Rayleigh's function. So actually F is half of dissipation, or rate of change of energy, or dissipation, 1/2 of dissipation power. And if we have this definition, it's very consistent with how we write the Lagrange equation. So if you remember, Lagrange was partial L partial Q dot I d over dt of this minus partial L partial Qi. We used to have Q prime I, but noting that Q prime is actually Q prime I is actually partial F partial Qi. So in this case, the equations, if we have dissipative forces only, and possibly some conservative forces as well, is going to look like d over dt partial L partial Q dot I minus partial L partial Qi. I'm missing some signs. Let me see. I have to double check. So I have it as plus here, partial F partial Q dot I equals 0. Let me think 1 second. I'm missing a sign. This must be negative. I'll have to double check this, but I think that is negative. In that case, this one is going to be negative, which makes sense. So F is kind of a positive number. If your force is dissipative, when you extract energy, the power coming out of system is, or power transfer with the system is negative. So this F is a positive number. And I think that works fine. So this one becomes negative. Yeah, all good. I think, I hope. I'll check. So this is the equations, the way we can write Lagrange's equation if we have dissipative forces as well, using these Rayleigh's dissipation function. So here is the kind of conundrum. Why do we do this? So we had Qs. We defined something bigger, called it F. And then instead of using Q's, we are now using F. What's the point? The point is that similar to whenever we were working with energy, it was easy. Working with forces was a little more cumbersome. Here we are working in an energy domain. It is sometimes a lot easier to find F rather than these Q's explicitly. To see that, maybe let's look at a very quick example. So let's pretend I have a system like this. Oops. Two masses with the springs and a damper in between, C. Let's put it here, C. No, C. And I have two generalized coordinates, Q1 and Q2. So what I can do is option one is find the force of this damper and translate that into generalized coordinates, which in this case isn't too bad, but we can do that. So find damping force. In this example, it's relatively easy, but in general, the next step from that damping force, finding the generalized coordinates along the two generalized forces along those two generalized coordinates, and from there get the equations of motion. That's one route. Option two is to stay in the energy domain, bypass kind of the force calculations. So I know my F, my Rayleigh function, is, let me see. It is 1/2 dissipation power and negative of that, let's call it this way. And I know my dissipation is the force value, the magnitude of the force, which is, let's call it C Q.1 minus Q.2. So the shortening velocity of this this damper multiplied by the shortening speed, or the force by the velocity by which the force moves, which is again same thing, Q.1 minus Q.2, and that is my Rayleigh's function, and I can very easily plug it back into the Lagrange, this now extended Lagrange equation, and I should be able to find the equations of motion. So, all right, so that is one class of these velocity dependent terms. So these terms where the velocity shows up linearly in the equations. In the next video, we will look at another class, completely different, but with very similar format. Those will be the gyroscopic forces or gyroscopic effects. So until then, I'll see you soon.